This is the first mini-lecture for section 3.5 of the textbook. We are going straight to section 3.5 right after section 3.1 because I feel that it is material that should follow closely behind section 3.1. Section 3.1, if you'll recall, was about historical numeration systems. Okay, some of those we saw were positional systems and some were not. At the end of that section, we talked about how our own system, the Indo-Arabic system, is a base 10 or decimal positional system. So I would like to just extend that conversation and talk about the possibility of using bases other than 10. The goal here is really to understand our base 10 system, but it's a little bit hard to talk about because you're so familiar with it. It's easy to take things for granted. So in this section, we're going to talk about using bases other than 10, and hopefully that'll help us understand the role that 10 actually plays in our positional system. So recall that in our base 10 system, everything is based on powers of 10, and our system uses 10 digits, the digits 0 through 9. Okay, those are known sometimes as the Arabian digits because, although they originated in India, people first came into contact with them through their contact with the Muslim cultures of the Middle East. So using this system, a numeral like 792 represents 7 times 10 squared plus 9 times 10 plus 2. So we're using 10 as the base here, but there's nothing special about the number 10 on its own. Okay, we have 10 fingers and 10 toes, so it's convenient for us to think in terms of tens. But mathematically, there's no reason why we can't use some other number as a base. There's nothing special about the number 10. So for example, we could just as well use a base 4 positional system. Okay, in the base 4 system, the numeral 312 would represent 3 times 4 squared, 1 times 4, and 2, which we usually write as 54. Okay, so we can illustrate it as follows. It's 3 4 squareds. So we need 3 4 by 4 mats, just like we use 10 by 10 mats in the base 10 system. Okay, but in the base 4 system, it's 4 by 4 mats. So we need 3 of those. Of course, that means there's 3 16s, which adds up to 48 in our system. Okay, so we have 3 mats, then we need 1 strip, 4 units long, 1 4, and then 2 units. Okay, that's how we represent 54 in this system. Okay, so these are just 2 different ways of representing the same amount, right? This represents what we usually call 54. When we say 54, we mean 5 10s and 4 1s because it's assumed that when we say something like that, we're using our base 10 system. Okay, but we could use the number 4 in place of 10. And in that case, to make up the same amount, we need 3 4 squareds, 1 4, and 2 units. That's 48, plus 4 is 52, plus 2 is 54. Okay, so if there's going to be any confusion between which system we're using, we just write the little number beside the digits. So we could write 312 base 4 for a base 4 numeral, 54 base 10, or simply 54 for a base 10 numeral. Okay, so these are just different ways of writing the same number. Remember we talked about how there's a difference between numbers and numerals. A numeral is a way of writing a number. Okay, when I talk about 312 base 4 and about 54 base 10, it's the same number. Okay, but the numeral is different. I'm just representing it in different ways, but it's the same amount. Just as the base 10 system uses 10 digits, the base 4 system uses 4 digits, 0, 1, 2, and 3. In this system, the digit 4 is not used. The number 4 is represented by 1, 0. And it's 1, 0 because it's 1, 4, and 0 ones. So 1, 0 is not 10 in this system, it's 4. So if you see a 1, 0 written in this context, don't say 10. 10 is this many. It's how many fingers you have. That's true no matter what system you're talking about. That word 10 refers to that amount. 10 does not refer to 1, 0. Okay, in our system, 1, 0 refers to 10. But in a base 4 system, it does not refer to 10. It refers to 4. So, you'll experience this if you teach young children how to write the numbers. They're typically fine with the numbers 0 through 9. Each has its own symbol. But when you try to teach a young child, let's say a 4 or 5-year-old, how to write 10, and you write down 1, 0, that's going to confuse them a little bit, probably. That's been my experience at any rate. They want to know, why is a 1 and a 0 suddenly 10? Well, it's because we're interpreting it that way. In our base 10 system, 1, 0 means 1, 10, and 0 ones. That's the explanation to give to a child. But if we're talking about base 4, 1, 0 means 1, 4, and 0 ones. Okay, so let's do a couple examples. Let's try to write the number 45 in base 4 notation. Okay, because 45 is a fairly small number, there's a couple ways you could go about this. One is to just try to draw a picture of it using mat strips and units. And I start with mats, and I just keep adding mats until I can't add anymore. So we've got one mat, that's 16. And then the second mat gets us up to 32. Okay, but a third mat would get us up to 48, which is too big. So there we stop with the mats. So now I start adding strips. So we're up to 32, remember. Okay, I add a strip. And now we're up to 36. And I add another strip. And we're up to 40. And I can add a third strip. And that gets us up to 44. If I added a fourth strip, that would get us up to 48, which is too large. But also remember that I'm not allowed to have more than 3 of anything, because we're restricted to these 4 digits, 0, 1, 2, and 3. Okay, so now I just add on a single unit. And that gets us up to 45. And I have 2 mats, 3 strips in a unit. So this would be 2, 3, 1, base 4. I could have also done this using long division, just like we did the Mayan and the Babylonian systems. So in order to do it that way, I would first probably want to list some of the powers of 4, which would be 1, If 4 to the 0 is 1, let me squeeze them in up here. 4 to the 1 is 4. 4 squared is 16. And the next power of 4 would be 64, which is bigger than the number. So, we would start with 16. Now divide 16 into 45. Goes in there twice. With 13 left over. So I need 2 16s. And then I would divide 4 into what's left over, 4 to 13. That goes in there 3 times with 1 left over. So I need 3 4s and a 1. 2, 3, 1. Okay, but I could have done it pictorially also because 45 is small enough. In our next example, 139, it's too large to do using just pictures. So let's begin by listing the powers of 4 again. 4 to the 0 is 1. 4 to the 1 is 4. 4 squared is 16. 4 to the third power is 64. Okay, 4 to the fourth power is 256. And, it keeps going that way. So I take the largest power of 4 that goes into my number. And then I just first see how many 64s do I need. So I divide 64 into 139. And it goes in there twice. I have 11 left over. So now I want to see how many 16s do I need. I can already tell I don't need any, but I'm going to go ahead and perform the division because I want to hold the place. Okay, so there are 0 16s that go into 11. Subtract and I get a remainder of 11. This helps me remember that I need 0 16s. Then I divide 4 into 11. It goes in there twice. The remainder of 3. So what I have here is 2 times 4 to the third power plus 0 times 4 squared plus 2 times 4 plus 3. If I add these all up, I get 139. And of course, the digits are going to be 2, 0, 2, 3. And again, this is in base 4. And the reason I couldn't do this using pictures is because it requires 4 cubed, and I can't draw a picture of that. That would be a cube. If I had manipulatives, maybe I could do that. 4 to the fourth, of course, so I wouldn't be able to do even with 3-dimensional manipulatives.